In this lecture, let's try to understand an application of combinatorics. One very nice application is the binomial theorem. So first, let's try to investigate how multiplication of two parentheses works out. So let's suppose that I had to multiply a1 plus a2 times, well, basically it's a pair multiplied by a triple. What would the multiplication look like? A little thinking, you will realize that we have additions that involve always a member from the first parenthesis and always a member of the second parenthesis. So for example, when I expand, I will have a1 times b1 plus a1 times b2 plus a1 times b3. So those are the possibilities involving a1 plus now the possibilities involving a2. So it's a2 and b1 and a2 and b2 and a2 and b3. So notice that our addition is of this form. So it's a summation where I have two boxes, box 1 and box 2. Always a pair, where the first box is filled by an A and the second box is always filled by a B. And this is over all possibilities. Look at it. Every possibility from here and every possibility from here. Every possible combination of either the first or the second with either first, second, or third of the second parenthesis. So it would look like this. Now, if we were to expand maybe a1 plus a2 times b1 plus b2 plus b3 times c1 plus c2 plus c3 maybe plus c4, just adding a bunch of numbers, it will be ugly to write the expanded form, but a little bit of thinking and you realize that the summation is over all possibilities where the first box is occupied by an A, second box by a B, and third box by a C. So here you have again A, here B goes, and here C goes. Can you count how many possibilities, how many terms are added, how many summands? So this is 1, 2, 3, 4, 5, 6. So 6 terms are added. And notice how do we get the 6? This can be thought of as an experiment where in the first box you pick either 1 or 2. So it's like this experiment, and observe that in the first box I have two possibilities. 1 or possibility 2 for a1 or a2. And for this part, I have 3 possibilities. It's either b1, or it is b2, or it is b3. So what do we get? We get by the basic principle of counting that there are going to be 2 times 3 terms that are added, summands. What about in this situation? Well, in this situation it's a basic principle of counting that has 3 experiments. And the first has 2 possibilities, the next has 3 possibilities, and the next has 4 possibilities. So it will be 2 times 3 times 4. The fact that the increase in order is coincidental. I just have 2 terms here, 3 terms here, and 4 terms here, but it will be the number of terms here. Those are the possibilities of filling out the first box. The number of terms here will be the possibilities of filling the second box. Number of terms here will be the possibilities of filling the last box. So let's see how that idea will give us a way to represent an expansion of this form. This is what we're interested in. We want a formula for x plus y to the power of n. What is that? Right? It's going to be x to the n, clearly, plus plus, I'm not sure how to write the terms in between. That's what I'm trying to ascertain, all the way to y to the n. How do we do that? So let's consider first what it means if I have x plus y. Well, there is no expansion, and therefore there is only, this is to the power of 1, you keep it like this, right? Now what about if I have x plus y squared? X plus y squared. How can I deal with that? Well, I can write it as a product of 2 parentheses, and I will indicate first parenthesis by giving the subindex 1. So it's x1 plus y1. And to indicate second parenthesis, I will say x2 plus y2. Then, based on that idea we just described before, that will be a summation where you have 2 boxes. Here is first parenthesis, and here is an input and only one input of second parenthesis. So in other words, here it has index 1. I place either x or I place y. Also here I either place x or y. So for example, if I, in this idea, if I have this box and here I have x and x, that in terms of the expansion corresponds to x1 times x2. Hopefully that's clear. So let's see what's going to happen now. If I were to expand this group, right, I clearly can gather how many x's I have. Based on, I have either 0 x's, in other words, I selected only y's, or I have 1 x, or I have 2 x's. So I can group the sum as follows, right? So that would be so 0x plus 1x plus 2x. There are no other possibilities. I either fill with y and y, that's 0x, or with 1x, or with 2x. That's how this formula will be formed, right? So how many ways are there to fill this with 0x? So that is only one way, right? So 0x times, I can say, I can place here simply y squared. That means I use 2 of them. And here I can write xy, because I had only 1x, the other had to be y. And here, since I have 2x, I can write x squared. And here I just have to put the coefficient. So how many ways can I get only y and y? Clearly I have to fill this box by a y, the first box, and the second also by a y. So there is only one way to do that. How many ways are there to fill in this box? Well, I have either this would be either x1, y1, y2, or y1, x2, correct? So one of the boxes is occupied by an x, the other by a y. So how many ways to do that? Clearly there are two. And here I have two x's, so clearly I had to, so here I had basically x1, x2. Here I had only, well, here I had, I'm sorry, y1, y2. And here I had x1, x2, right? So this is also y. So I see that I get the coefficient 1, the coefficient 2, and the coefficient 1 again. Okay? What is the nature of those coefficients? How can I figure out what are they in general? So in general, how do we expand x plus y to some arbitrary integer power? We can try to use that same idea. We see x plus y to the n. We can break it into individual parentheses. In each parenthesis there are, we can indicate the parentheses by giving the subscript 1 to the first parenthesis and to its members, 2 to the second parenthesis, and to its members, and all the way to n for the last parenthesis. And when you realize how multiplication works, the summands, the terms that are being added, will consist of, you can break it into n boxes. And in each box, in box 1, I either have x or y. That's the contribution from first parenthesis. The second box is a contribution from second parenthesis, either x or y again. And all the way to the last parenthesis, it's always either x or it is y. So we sum up terms that are multiplications from one and only one term out of each parenthesis. One representative is selected, either x or y in here, either x or y in here, for each parenthesis, and we sum over all possible combinations of delegates from each parenthesis. So when I look at the summation, I can group it based on how many x representatives arrive. Right? From the first country parenthesis, how many x representatives arrived. From the second parenthesis, how many representatives arrived. So I see this. This means only y representatives arrived from each parenthesis. That's y to the n. So this is x to the 0 power, right? So I can group the sum based on no x's, 1x, 2x, 3x, in general, kx, and then n minus ky, right? It's always the number of x's plus the number of y's always equals n. So how many terms are going to be here? Well, let's suppose that y means that, well, so this has actually a very interestingly, this has much to do with the current situation. So classes were cancelled and no students are coming. Those are the possible attendance rosters. So if I have n students, let's say that would be student 1, this is student 2, all the way to student n. So this coefficient of y to the n counts how many possibilities are there where all my students have arrived. That means all the students have been selected. So if all the students are present in the class that are registered for the class, then I can imagine this box, and this box lists first student, that's first parenthesis, second student, second parenthesis, third student, and onwards. And this means that they all present, right? So y, if y was limited from this parenthesis, student 1 came. Yes, he came for second student. Yes, the second student and the third student came, and all of them are yeses. So this is a box involving yeses and x's for having been absent. So there is only one way to fill the string with only y's. So you can say this would be 1. Now, for the next situation has all but one individuals came to class, right? So this is an attendance roster where there is an X for one of the students. So how many possibilities are there? Well, I can choose which students came, right? So I have for that n students, and I choose how many were absent. So n choose 1. Then n choose 1 attendance rosters, or n attendance rosters, where some student was absent. So for example, that would look like this. So first student, let's say first student is absent, and the others are all present. Right? Or maybe it is first student is present and second student is absent, and then the rest are present. Okay? So you can see that that I choose the one that was, it's like choosing a subset. So I choose those that were absent. And choose 1, I chose those that were absent. Now here, 2 people were absent. So how many possibilities? The same number of possibilities as n choose 2. And in general, this means k individuals were absent. So it means that out of those n students registered for the class, k will have to be mapped with x. So n students choose those that did not come to class, and choose k is the arbitrary coefficient for xk times y to the n minus k. Right? Because I choose the students that are absent. Now, what is our last coefficient? Well, our last coefficient is unfortunately the dire state in which we are. Not a single student came. In fact, not a single student will come to the very end of the semester. So what does it mean? It means all students are absent. I take n and I choose n. How many ways to choose n? That means 1, right? There's also one way to do that. And this one is, of course, n choose 0. What have we understood? Well, so look at it. We now have a formula. This means that x plus y to the power n can be broken into the different type attendance rosters from k equals 0 to k equal to n. Here I have x to the k, y to the n minus k. So this coefficient, you can think of, it represents the situation where k students were absent and n minus k students were present. How many possibilities are there? This is as many as the ways to choose the absent students. So out of n individuals, I have to choose k. And here is my binomial formula. Let's see if we understood this principle. I want you to simplify this sum. What is n choose 0 plus n choose 1 plus n choose 2 onwards all the way to n choose n consecutively, if I add it this way? Well, there are two solutions. So first you might observe that those are the coefficients of the binomial theorem, and realize that what we're writing here is summation of k starting from 0 all the way to k going to n. That's just a shorthand for summation. And here we are getting the coefficients n choose k. And notice each coefficient here is 1, so I might insert here a 1 to the power of k. And here I might insert 1 to the power of n minus k. Now, this looks exactly like a binomial theorem where x equaled 1 and y also equaled 1. So that looks like the expanded form of 1 plus 1 raised to the nth power, which is nothing more than 2 to the nth power. Pretty simple, right? Well, we could have done it even faster. What is this sum counting? So suppose that, well, you look at this pile and you realize that somebody was talking about a very particular, very simple situation. What that might say. So this is what I perpetually worry about. I have n students and nobody comes, 0 students. So that's a possibility of where my attendance roster is empty. Then the second possibility here is how many rosters, how many attendance rosters do I have where out of n students only 1 shows up? How many rosters where out of n only 2 show up, and so on. So you realize that this is just a bunch of piles that on each pile I have a code, right? And this code is that of is the attendance roster. So this is box for student 1, this is box for student 2, box for student 3, all the way until student n. And in each box I will put in 0 for absent or 1 for present. So there are like n experiments, and this can receive either a 0 or 1, and any of them will receive either a 0 or 1, depending whether, in this case, student n came to class or did not come to class. So that means we have n experiments, and in each experiment I have 2 possible results. So how many possibilities are there? Well, by basic principle of counting, 2 times 2 times 2 all the way until the very last one. So it's 2 times 2 times 2 times 2, where I have this n times. And that equals to 2 to the n. And again, how do I get from that the sum? So this is calculating the attendance rosters, all the possible strings of 0s and 1s that can fill in this box. But I then can group them into piles. So I can look at the attendance rosters. This represents the attendance roster where all the inputs are 0s. This represents the collection of all attendance rosters where all the inputs are 0 except for one input. There is only 1 copy of number 1. Only 1 person came, right? So we have lots of 0s, and only in 1 input here, only in 1 box, there is a 1. Here, lots of 0s, but 2 inputs contain 1. And so on, right? And the very last one is a string that contains only 1. So this is just adding the piles, arranging them by a number of students that came to class, and this is all of them together. Now, here is a very useful identity. So the way we solved this problem before, that's called combinatorial analysis. You look at the formula and realize what method was used to count. And then you devise another method of counting like we did over here. And because the 2 methods are counting the same things, the 2 formulas obtained must be identical, must be equal. So here, let's try to see how that might work. Here's the useful identity. So I want to prove that n choose r equals n minus 1 choose r minus 1 plus n minus 1 choose r. I can do it the hard way by algebra, but that's boring. I can realize those formulas are the same in the following way. So suppose that I have n students, and one of those students is my favorite, Jimmy. So Jimmy is my favorite student, and I have to create a delegation of r students. So what happens over here? So this is just how many choices are there to pick r students out of n individuals, right? So that's n choose r. We already devised that formula. What is this? This here is a number of ways to choose Jimmy among my delegation and additional r minus 1 students. So that means Jimmy is in the delegation, he's a special student, and this consequently means that Jimmy is out. He's not part of the delegation. Again, among the R students chosen, I have those students that contain Jimmy and those that do not contain Jimmy, right? So I can imagine that when I report who came, here is how I see my report, right? So this will contain R integers in increasing order. So let's say that Jimmy is labeled with the number 1. And the other students are 2 all the way to n, right? So if I have the numbers in order, I group in this pile all the strings that begin with the number 1. So for example, 1, maybe 3, 5, etc., right? So that means Jimmy is in the delegation. Now, that's the number of such delegations, since they are all of size r. So this number is picked. It's one number is accounted for. I have additional n-1 numbers, out of which I need r-1 numbers picked to complete my collection of r numbers. And over here, the numbers do not include 1. So maybe the number is 4, 7, I don't know, 9, and onwards, okay? So that means I have to have a full collection of R numbers, but 1 cannot be a number there. So that's how I break it up. So let's see if we understand the matter. Here is a similar idea. So we have this complicated looking formula and we want to see if we can figure out a simpler formula. So we have n choose r multiplied by n choose 0 plus n choose r minus 1 multiplied by n choose 1. And you can see that r is losing an integer each time I move through addition sign, and the lower number under m is gaining an integer. So this is the formula written out together. How might we come up with a story argument, a combinatorial argument, that will make us right away see what this formula is counting? Pause if you want to think about it and try to come up with your own formula. Let's see how we do that. Okay, so notice I have n and m. Let's say that m are my special favorite students. And let's say I'm going to invite r individuals from my class consisting of n plus m students. There are n students that are okay and m students that I especially like. And out of those students, I'm going to invite, out of all of them, r students to go with me to Greenwood Cemetery. So what are the possibilities? So the possibility is that none of the students that I like come, and all the r students that are coming are from the other group, or exactly one of my favorite students comes, and r-1 students from the other category come, or 2 students that I like come, all the way to all the students that I like come and none of the other students, right? So that's n plus m choose r. So in here I had only one special student, Jimmy, and here, very similar question, but I have m Jimmys. So that's n plus m choose r. So we can make use of that Jimmy identity to come up with Pascal's triangle, a very quick way of expanding powers of x plus y. So the Pascal triangle is constructed as follows. So you write a 1 on the top, and then you form a triangle by writing 2 1s on the sides. And then to write the next level, you put a 1 in here on the side, and then you look at this one and that one, you add them together. So, and you put in between, you put the number 2. So 1 plus 1 is 2, and you complete it with 1. Now to go to the next level now, you put out another 1, and then between 1 and 2, you take 1 plus 2, and you write a 3. And then between 2 and 1, you add them, and you again write a 3. And then you place a 1 in here. And you can continue in this fashion. So next level would be 1 in here. And then 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. You see, always between the two numbers on top of it, I have a 4 now, and then 1. Now notice what it does. So this tells me, this row tells me that, for example, x plus y raised to the power 1 simply has the coefficient 1 times x plus 1 times y. This tells me the coefficients of x plus y squared. It tells me put 1 next to x squared plus put 2 next to x times y, and then put 1 next to y squared. Okay, so I begin with x to the biggest power, then I have x to powerless, and I go until x has no powers left. So this third row has x plus y cubed, and that tells me, well, begin with x cubed and put 1 in front of it, plus, well, you guessed it, now it's 3 times x squared and y. You see, I took 1 power from 3, now it's 2, and I gave it to y. The power of x plus the power of y always equals to 3. Plus the next is against 3, so we have x now to 1 power less, and we have y squared. Finally, 1 times y cubed. What about the next row? Well, that is x plus y to the power 4. And what we get is 1 times x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4. Seems easy, right? Why does this formula work? Well, let's look at the level. Let's just look at one of the levels. Let's say 1, 2, and 1. What is this number? This number is 2. Choose 0, yes? 2 choose 0 will be 1. This number is 2 choose 1. And this number is 2 choose 2. Now, the coefficients for the cube formula should be what? They should be 1, which equals to 3 choose 0. Then there should be 3, which happens to equal to 3 choose 1. And another 3, which happens to be 3 choose 2. And finally, 1, which in this case happens to equal to 3 choose 3. Okay? How are they related? Look at the Jimmy formula. The Jimmy formula tells us that if I have, let's say, if I want to know what is 3 choose 1, 3 choose 1 is the sum of 3 minus 1, which is 2, choose 1 minus 1, which is 0, plus 3 minus 1, choose 1. So you see, the sum of those coefficients will give us 3 choose 1. Similarly, if I want to figure out what is 3 choose 2, so that means I need to subtract 1 from 3, so I'm going back to a higher level, so I look at 2 choose something, and first I have 2 choose something and choose whatever the number used to be, also minus 1. So it will be 2 choose 1 plus 2 choose 2. So you can see that Jimmy formula allows us to very quickly recursively calculate the coefficients of n choose k. So we also have the n choose k for each k here, and the coefficients of the expansion of x plus y to the nth power.